Okay, so for today we will start on new chapter. So last chapter we have learned about one plot of the system transfer function using root locus. Okay, so in chapter 5 we will go into two more types of plots, which we call it frequency response techniques. And the two plots are Bode plot and Nyquist plot. Okay, so for today we will go into Bode plot, and tomorrow maybe we will go through with Nyquist. Okay, so in this topic, students will be able to recognize what is the gain margin and phase margin frequency using Bode plot, and determine the stability through gain margin and phase margin using Bode plot. And then for tomorrow, we will go through the same thing but using Nyquist, and also using Nyquist in determining stability. Okay, so let's go through with Bode plot. So a Bode plot is basically a graph, but the axis is in terms of logarithmic, okay, logarithm, meaning that your graph right now, the axis is has the same distance between the points, okay. But in Bode plot, it uses graph with logarithm axis. So the axis will be in terms of log frequency, the frequency of the system, but we apply log, okay. So it is usually combined with Bode magnitude plot. So this is expressed in decibel. Okay, so this is also used log. Later we'll see example what is decibel, and also Bode phase plot. Okay, and this is the angle or the angle or phase of the transfer function. So we have you already know that transfer function can be described in terms of magnitude and angle. Okay, so the magnitude in Bode plot we will use decibel, and the angle we retain the same angle in degree, and we call it phase. Okay, phase shift of the Bode plot. Okay, so Bode plot are commonly used to display frequency response, because frequency has a long range of values from zero until maybe thousands. So it's difficult to plot in single usual graph, because your graph maybe if in one A4 paper, maybe it can be up to maybe until 20 values, 20 unit, but frequency can be up to thousands, maybe 1000, 2000. So if we use log, we can reduce the number of the length of the graph, so that we can plot more frequency in one graph. So that's why it's easier to use Bode plot to represent the frequency response. Okay. And Bode plots are frequency response. Okay, so it has gain and phase margin that is displayed in two separate plots. So we have just now I mentioned we have magnitude Bode plot and phase Bode plot. Okay, so there are two types of Bode plots. So usually the horizontal axis or the x-axis, we plot the frequency, but in log scale. Okay, so we use log. Usually log 10. Okay, in your calculator we have log 10. Okay, and then the vertical axis we use for gain and describe in decibel. So for decibel we use 20 log 10. Okay, so for frequency we use log 10, and for decibel we multiply with 20. So why 20 log 10? That's decibel. Okay, I don't know why. Maybe you need to read from Wikipedia. Okay. Okay, so this is an example of Bode plot. So we have the top one is the magnitude Bode plot. So it is in terms of 20 log, and then the bottom one is phase or angle in terms of degree. So this is an example of Bode plot for a transfer function. And if you look at the graph, the lines here, it is not the same as your usual graph, okay, kertas graph yang biasa, because the distance is different as the frequency or the x-axis increase. So the x-axis increase by scale of 10, okay, from 0.1 and then 1, 10 and then 100. And then the graph, if you see, the scale becomes narrower or closer to each other. Okay, and for the y-axis, it remains the same. Okay, only the x-axis has different in terms of the distance between the lines. Okay, so the first thing that we need to know about Bode plot is to find gain margin frequency. Okay, gain margin frequency is the frequency at 180 degree of phase. Okay, so you need to remember gain margin frequency is the frequency at negative 180 degree phase. And then another thing is gain margin. So gain margin is the change in open loop gain expressed in decibel required at 180 degree of phase shift to make the closed loop unstable. Okay, basically using Bode plot, gain margin frequency. At gain margin is defined as the gain required to raise the magnitude to 0 decibel. Okay, so let's look at example or figure on how to visualize this. Okay, so your gain margin frequency, this one. Okay, so this is your gain margin frequency, and it's the frequency at 180 degree of phase. Okay, so when you have a Bode plot, you just need to look at 180 degree phase and then find the frequency when your Bode plot intersect 180 degree. Okay, and then at 180 at the gain margin frequency, at this frequency, then you need to look at your magnitude Bode plot. Look at your magnitude Bode plot and determine the difference between 0 decibel and this point here. So the difference between these two is known as gain margin. So this is gain margin, and the frequency at gain margin is the gain margin frequency. Okay, so these two are two things that you need to know how to look for in Bode plot. And then another thing is phase margin frequency. So phase margin frequency is defined as the frequency at magnitude 0 decibel. And then phase margin, if you use Bode plot, phase margin is defined as the difference between the phase at phase margin frequency and 180 degree. Okay, so let's look at some visual on how to understand this. Okay, so phase margin frequency, this one. Okay, this is your phase margin frequency. Is the value of frequency at 0 decibel. So when your Bode plot intersect 0 decibel, then the frequency is the phase margin frequency. And then to find the phase margin, basically you look at the phase plot. So this is phase plot. And then at the phase margin frequency, you determine the length or the difference between this frequency and 180 degree. Okay, so that's phase margin and phase margin frequency. So these two are important in determining the stability of a system, okay, using Bode plot. So if you look at this example, so first thing you need to look is the gain margin. Okay, so first you need to find the gain margin frequency. So gain margin frequency, this one, WPC here, is the value of frequency at negative 180 degree of phase. Okay, so negative 180 degree phase, you get gain margin frequency. And then from gain margin frequency, you look for the gain margin. So basically the difference of this plot from 0 decibel. So how much is the difference is the gain margin. And then for phase margin frequency is the frequency at 0 decibel. So this is 0 decibel. So the frequency at 0 decibel is the phase margin frequency. And then to find phase margin, basically you look at the phase margin frequency. How much is the difference of phase margin phase from negative 180 degree. So this one is the phase margin. Okay, so how to determine stability of a system using Bode plot based on gain margin and phase margin. So omega 180 degree is your this is gain margin frequency, and this is phase margin frequency. So if phase margin frequency is less than gain margin frequency, so the system is stable. Okay, simple. And then if the phase margin frequency here is bigger than gain margin frequency, then the system is unstable. Okay, so the condition is phase margin frequency must be less than gain margin frequency. Okay, let's look at an example on how to draw Bode plot. Okay, so let's say you are given a unity feedback system, and GS, the forward transfer function, equals this one. Okay, so the question may be asked you to draw the Bode plot and phase plot, and then evaluate the gain margin, phase margin at 0 frequency and 180 frequency, and then determine the stability of the system. Okay, if you look at your quiz 13, I already list the steps required to plot Bode plot and then to determine the stability. Okay, so just follow this step, and then you can plot the Bode plot. Okay, so the first step is you need to convert every S equals J omega. Okay, so for example, this transfer function, so each S becomes J omega. So we can write this in terms of J omega. Okay, after that, you need to look at you need to substitute omega given in the question. So in this question, you are not given any omega, but most of the time, the question will give you some omega. Okay, such as in this example, in this quiz 13. Okay, I give you some omega value. So if you are not given any omega, as in this example, we use variety of values of omega. Okay, so in this example, So this example actually do for omega from 0 and then increase slightly and then up to maybe 10,000. Okay, so this is just example. So after you substitute s equals j omega, then you need to substitute omega for each frequency given. Okay, for each poles and zeros uh, from the transfer function. So for example, if omega equals 0, then you start with this one first, the first s plus 5 here. So s plus 5, basically you have j omega plus 5. So when omega equals 0, then this becomes 5. So from here, you determine the magnitude of this number. So if you plot in S-plane, 5 will be here. So the magnitude is 5. So you get 5. And then the angle is 0. Okay, so angle measured from real axis, positive real axis. So you get 0. And then you repeat the same process for each of the numbers or the bracket. So the second one is s plus 20. So you substitute j omega, s equals j omega, and then try to determine the magnitude and angle. Same for s plus 50, and same for 10,000 here. After you have determined the magnitude and angle, then you need to determine the overall transfer function magnitude and angle. So the magnitude, to determine the overall magnitude, basically you use a product of 0 divided by product of poles. Okay, the product of magnitude. Okay, so here 5 times 20, 10,000 divided by 5 times 20 times 50. So you should get 2.0. Okay. Okay, so you get 2. And then angle, for angle, basically you use the formula sum. Summation of angle at 0 minus summation of angle at pole. So this formula is the same as the one in root locus. Okay. So you sum the angle at 0. So 0, angle at 0 is 0 minus angle at pole. So 0, 0, and 0. So you get 0 angle. And then after you find the overall transformation, then you need to convert the magnitude in decibel. So this one is in decibel. So you use 20 log m. So you get 6.02. So this is the value that you want to plot later in your Bode plot. Then repeat the process for different omega. Okay, so you use omega equals 0.1 and then find the magnitude and angle for all of the pole and 0 and then find the overall transformation and then in terms of decibel. So if your question, let's say in the quiz, you are given a certain value of frequency. Okay, like 0.2, 0.7, 1, 6, and 30. So you only need to do 5 calculations for the magnitude and angle and the overall magnitude and angle. Okay, after you get all these values, you tabulate the values, then you can plot the Bode plot manually. Okay, in log graph. If you are given log graph, if you are not given, then draw in kertas kajang lah. Okay, A4 paper. Okay, so after you get this value, then you plot. So this is an example of the plot. Okay, so this is magnitude plot, and this is the phase plot. Okay, so if you take more points, more value of frequency, you will get a smoother graph. Okay, but this graph is tak berapa cantik lah. So after you get this graph, then you need to determine the gain margin and phase margin. So ini example taken from MATLAB, okay? So the same question. So for gain margin is the frequency, the gain margin frequency is the frequency at negative 180 degree, okay? So negative 180 degree, you get gain margin frequency here. So here is gain margin frequency. And then the difference between the gain and 0 decibel at gain margin frequency is gain margin. So roughly you get a 19.7 at frequency 36.8 radian per second. And then the next one is phase margin. So phase margin, first you need to look at phase margin frequency. So phase margin frequency is this point. Is the frequency at 0 decibel. And then phase margin is the difference between the phase at phase margin frequency with negative 180 degree. So roughly you get 92.9 degree at frequency 7.74. So stability is when phase margin frequency is less bigger less from gain margin frequency. So the system is stable. Okay, any questions so far? Okay, so if you have no question, then that's it for today's lecture. Okay, so the example given in the slide, basically the same thing as the previous example, but more focus. Okay, because the example give you only certain frequency value, and you need to do table method and plot in the kertas graph. Okay. So same thing for example 3. So the only difference is that in the example, you are not given the question as in the quiz to determine the stability from gain and phase margin. Okay, so maybe the difficult part is to determine gain and phase margin. Okay, so actually that's it for today's lecture, half an hour only. So if you have any question, you can ask me. If no, then that's it for today. And we continue tomorrow for night quiz plot. Okay. All right. So that's it for today. Assalamualaikum and bye.
Terima kasih, Doktor.